cover the basic aspects and we'll move on to the previous set questions. Okay. So firstly, we have some historical developments in the field of chemistry. Okay. Initially, the chemistry was basically the science of whatever's around you, mixing it and checking how things work out, how the chemicals react, how they behave. And it was a mixture of legend, myth, along with some science also. There was a philosopher's stone which could convert metals into gold, and there was an elixir of life which would grant immortality. So both of them were initially the, you know, search. They were the cause of why chemistry developed, because everyone wanted to search for these two things: the philosopher's stone and the elixir of life. Okay, so in India, the chemistry was called Rasayan Shastra, Rastantra, Raskriya, Rasvidya. And there are many scientists, okay, who have contributed, and there are many texts, okay. Rigved, Arthashastra, okay, Charak Samhita, Rashopanishada, Rasratnakar, Sarvanam, and there were other texts like Brihat Samhita. Okay. Then there were some scientists, for example, Varahamihir, Gandhayakuli, and others. Okay, Kautilya and all, Charak. So we don't have to remember their names, but we should basically know. So the modern chemistry, let's move on to the modern chemistry. The modern chemistry began when the atoms and molecules were discovered. Okay. What is the use of chemistry? The use of chemistry is it gives us life-saving drugs like cisplatin, Taxol, AZT. Then there is the chemicals, like they help in technology. For example, superconducting ceramics, conducting polymers, optical fiber and all. These are all technological devices. Then acid, alkalis, dyes, polyester and all. The industries, they contribute to the economy. Okay, so this is the importance of chemistry. It is basically related to the economy of the country. Next, we move on to the states of matter. The states of matter, as you're aware, there are three states of matter: solid, liquid, and gas. Although two other have been discovered, but we focus in chemistry in these three. Okay. Solids have a definite volume and shape. Liquids only have a definite volume, no definite shape. And gases do not have a definite volume and don't have a definite shape. Okay. Next, we go on to classification of matter into mixtures and pure substances. Firstly, we have a mixture. What is a mixture? Mixture is there are more than one substances in a mixture. It contains particles of two or more pure substances which may be present in any ratio. Okay. Then there are two types of mixture: homogeneous and heterogeneous. In homogeneous, the components completely mix with each other. So if you just take a spoonful from a homogeneous mixture and you analyze the composition, it will be same throughout the mixture, whether you take a spoon from the top or you take a spoon from the bottom or from any other side, it is the same. Then there are heterogeneous mixture. The composition is not uniform in heterogeneous mixture. So it might be variable on the top of the mixture and on the bottom of the mixture or any pair on the mixture, but it is not constant. So if you take and analyze a composition from a particular part, you will find that one pure substance is more in a particular area and in another area it is less. For example, mixtures of salt, sugar, grains and pulses along with some dirt are heterogeneous mixture. And similarly, the composition of example of homogeneous mixture is a sugar solution and the gases in air. Next, apart from mixtures, we have pure substances. Pure substances are like the constituents have fixed composition. Okay, they are atoms, molecules. Okay. Now the pure substances, they cannot be separated by a simple physical methods. You cannot just boil it and separate it. You cannot just, sieve it or filter it and separate them. They need chemical methods for separation. They can further be classified into elements and compounds. Okay, we can see elements and compounds. Okay, so elements are only consisting of one type of atom. So elements have only one type of atom, and these atoms may be single, they may be singularly arranged like this, or they may be associated with each other of the same type, like this, or like this. If they are singular, they are known as elements. If they are like associated with each other, they are known as molecules. Okay, next we have a compound. Compound is made up of more than one element. Okay, for example, the examples of elements and molecules are, see, atoms of different elements. We can see hydrogen, oxygen, nitrogen, copper, sodium, and then if two hydrogen combine, we get a H2 molecule. If two oxygen combine, we get a O2 molecule. Examples of compounds, we have water and carbon dioxide. See, in water we have two hydrogen and one oxygen. In carbon dioxide we have one carbon and two oxygen. So this was all about matter. Now we come to the properties of matter. There are physical and chemical properties. So physical properties are the ones which can be measured without changing the identity of the composition of the sample. Like, we don't need to change the substance in order to see a physical property. Physical properties, for example, the density, the boiling point, the melting point. All right. So these do not your substance. Then we have the chemical properties. The chemical properties require a chemical change to occur. Then only we can measure a chemical property. Chemical properties may be reactivity and oxidative nature or reducing nature. Okay, these are chemical properties, which, for example, combustibility, acidity, or basicity. How much acidic it is, how much basic it is it combustible, to what extent? For this, we have to burn a substance, or we have to react a substance with another substance. Okay, so now we go to measurement of physical properties. So earlier there were the English and the metric system, but now we have only one system, which is the International System of Units, or SI system of units. So the SI system has 7 base units. Let us see one of them, each one of them. Okay, firstly we have length. Okay, and the unit of length is meter, SI unit. Then we have mass. Unit of mass is kilogram. We have time, unit is seconds. We have electric current, the unit is ampere. We have thermodynamic temperature, and unit is Kelvin. Amount of substance, unit is mole. Luminous intensity, unit is candela. So these are the fundamental or basic physical quantities. Other physical quantities can be derived from, multiplying or dividing these basic physical quantities. For example, density we can get from dividing mass by volume. Volume is length squared thrice. Okay. Next, we have definitions. These are how a unit of each fundamental base is defined. Okay. So we will skip this. We will directly move on to mass and weight. Mass and weight. Mass is the amount of matter, and weight is the force exerted by gravity on the object. Both are different. So weight is weight can be variable in different places in the universe, but mass of the object is constant. Mass is the amount of substance, amount of substance that the object holds, and weight is the force of gravity exerted on the object. Then we have volume. Volume is the space occupied by the object. That is very simple. Density is mass divided by volume. We know it. Temperature, we have 3 scales for temperature. We have the Kelvin scale, we have the Celsius scale, and we have the Fahrenheit scale. So how to compare them how do we know what is Kelvin, which is Kelvin? So first we know that Celsius is widely used in India. So we will see Kelvin is equal to degree Celsius plus 273. Okay. This is the formula for Kelvin. And Fahrenheit is 9/5 degrees Celsius in plus 32. All right. So this is Fahrenheit. So if we unite all of them, then Fahrenheit minus 32 upon 9 is equal to Celsius upon 5 is equal to Kelvin plus minus, Kelvin minus 273 upon 5. So this formula, if you remember, then you will be at ease in temperatures. Next, we have uncertainty in measurement. All the measurements are uncertain to a certain degree. We measure them and basically it is a part of physics, how to measure the uncertainty. We have the scientific notation, which is basically, if there are so many zeros, how to denote them. We just express them in powers of 10. We have, and then how to multiply and divide these powers of 10. Then we have significant figures. We have a few rules for significant figures. What are them? So first rule is all the non-zero digits are significant. For example, in 285 centimeter, there are 3 significant figures. In 0.25 ml, there are 2. Zeros preceding to first non-zero digit are not significant. So 0.03 has only 1, 0.0052 has only 2 significant figures. So if there is a non-zero digit, all the zeros preceding it are not significant. But zeros between two non-zero digits are always significant. So if 2.005, there are 2 non-zero digits, and in between them, as many zeros as we put, they will be significant. Fourth is zeros at the end or at the right of a number are significant. So 0.200 has 3 significant zeros. Okay, but 100 has only 1 significant figure. Wait, 100 has only 1 significant figure, but 100 has this is a printing mistake. We just ignore this. 100 has 3 significant figures and 100.0 has 4 significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 into 10 to the power 2 figure, 1.0 into 10 to the power 2 for 2 significant figures, and 1.00 into 10 to the power 2 for 3 significant figures. So this is like how we can express a number for according to significant figures. Next, counting the numbers of objects for 2 balls or 20 eggs have infinite significant figures, as they are exact numbers and can be represented by writing infinite number of zeros after placing a decimal. 2 balls, 20 eggs, 20 girls, 20 pens, 3 sunglasses, okay, 5 tables. All these are infinitely significant. We can put as many zeros after a point in them because they are accurate numbers. So these 5 points we need to remember. Then multiplication of division, there are some rules which you need to remember, and then we have some examples. Then comes one more important concept, law of chemical combinations. So there are some 4 or 5 laws which we need to remember, which govern how chemicals combine with each other, how chemicals form compounds, right? How elements form compounds. First is law of conservation of mass. It was put forth by Anton von Lavoisier, and it says matter can neither be created nor destroyed. So this is the statement that a matter, it cannot be created or destroyed, so it is conserved. The total mass of universe is conserved. Okay. Next, we have law of definite proportions. Okay, this law was given by French chemist Joseph Proust, And this law states a given compound always contains exactly the same proportion of elements by weight. So what does that mean? See, it means that if a compound is there, it always contains the elements in the exact composition by weight, in the exact proportion by weight. So if you take water from two different sources in the world, suppose you take water from a lake and water from ocean, it will always be H2O, hydrogen is to oxygen will be 2:1 by number and 1:8 by mass. That is constant. Okay, that is law of definite proportions. So law of definite proportion is for the same compound. Next, law of multiple proportions. It is a bit modified. It was proposed by Dalton. It says if two elements can combine to form more than one compound, the masses of one element that combine with the fixed mass of the other element are in ratio of small or whole numbers. So if two elements are forming more than one compound, suppose H2O and H2O2, H2O, H2O2, these are two compounds formed by hydrogen and oxygen. So suppose we fix the mass of hydrogen. We fix the mass of hydrogen by 2 grams. So for H2O, for 2 grams of hydrogen, how much oxygen do we have? We have 16 grams oxygen. Similarly, in H2O2, for 2 grams of hydrogen, we have 32 grams oxygen. If we take the ratio of 16 and 32, it will always be a whole number ratio, 1:2. Okay, that is what this law says. It's a bit uninteresting and a very basic kind of law which has been twisted, but we need to remember it. Next, we have Gay-Lussac's law of gaseous volume. It says when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided that all the gases are at the same temperature and pressure. Thus, 100 ml hydrogen combined with 50 ml oxygen to give 100 ml of water vapor. So all of them are in simple ratio. Then we have Avogadro's law, volumes of all gases at same temperature and pressure contain equal number of molecules. So if there is a hydrogen and oxygen at the same temperature and pressure, they should contain same number of molecules. This is Avogadro's law. Then there is Dalton's atomic theory. It says matter consists of indivisible atoms. All atoms of a given element have identical properties, including identical mass. Compounds are formed when atoms of different elements combine in a fixed ratio. Chemical reactions involve reorganization of atoms. The atoms are neither created nor destroyed in a chemical reaction. Okay. And this theory could explain almost all the chemical properties shown by the chemicals at that time. So it was widely read. Then we have atomic mass, average atomic mass. Average atomic mass basically depends on how much abundant an isotope is, and that is how much you expect. What is the expectation of the atomic mass that you would get if you naturally occurring element. Then there is molecular mass, mass of one molecule. Formula mass is mass of one molecule in an ionic compound. Then we have the mole concept. What does the mole concept say? The mole concept, it basically says that it says that the mass of 1 mole, it says that there are equal number of atoms or molecules in it is basically a modification of Avogadro's law. It says there are equal number of atoms and molecules in a gas at the same volume, and at they have defined a fixed number of atoms which is there in 1 mole of compound. So for 1 mole, how many atoms or molecules are there? It is the Na, it is the Avogadro's constant, and the value of this constant is 6.022 10 to the power 23. So if 6.022 into the 10 to the power 23, same types of atoms or same type of molecules or same kind of substances are grouped together, they will consist of 1 mole of substance. Okay, 1 mole is basically the amount of matter or the number of elements. Okay, having defined the mole, it is easier to know the mass of 1 mole of substance. The mass of 1 mole of substance is called its molar mass. So if what we said about molar mass, it is the mass of 1 mole of substance. So atomic mass is the mass of one atom and molar mass is the mass of a mole. Molar mass of water is 18.02 gram per mole. Sodium chloride, it is 58.5 gram per mole. Okay, so for everything we can calculate the molar mass. Then there are percentage compositions. For H2O, we can find out the percentage composition by mass. We can suppose for hydrogen, 2 gram of hydrogen in 18 gram of water, right? And we find the percentage composition. How much percent? It is something 11.2%. For oxygen, 16 gram per 18 gram of compound, it is 88.8%, right? Then we have empirical and molecular formulas, which we would be covering soon. Stoichiometry. What is stoichiometry? Stoichiometry is basically balancing the chemical reactions. For balancing the chemical reaction, you need to know which one is the limiting reagent. Okay, if amounts of reactants are different than the amounts as required by a balanced reaction, one reactant is more, it may be more in amount than required, might not get exhausted in the reaction because the other reactant might be less. And this reactant is known as the limiting reagent because this will get completely exhausted in the reaction. And after this is exhausted, no more reaction will be occurring. So we need to find out the limiting reagent for performing stoichiometric calculations. Then reactions and solutions. What all concentration terms we can expect? Mass percent or weight percent, mole fractions, molarity, molality. All these are important because they tell us the chemical concentration in solutions. Okay. What is molarity? Mass percent is mass of solute divided by mass of solution into 100. Mole fraction is moles of a compound divided by total moles into, just moles of a compound divided by the total moles in solution. Then molarity is moles of solute divided by volume of solution in liters. Finally, we have molality. It is moles of solute divided by mass of solvent in kilogram. Right. So let us move to the previous year questions right then. So I've prepared a few questions for you guys. These are from the last year's JEE-Main January attempt. First question says, when Fe.93O is heated in presence of oxygen, it converts to Fe2O3. The number of correct statements from the following is. First statement is equivalent weight. So to find out the equivalent weight, we need to find out the change in oxidation number. Change in oxidation number is delta On is the change in oxidation number into moles. So if Fe 0.93, the charge is plus, the charge is, we need to find it out, it changes into Fe2O3 where the charge is plus 3. The charge in Fe 0.93O will be 2 upon 0.93 and the change in oxidation number will be 3 minus 2 into, we will divide it by the total number of moles. Okay. So if we do the calculations, this will come out to be Okay. That is 0.79. So this is exactly correct. First statement is correct. We have molecular weight divided by 0.7, which is the n factor. Then number of moles of Fe plus 2 and Fe plus 3 in 1 mole of Fe 0.930 is 0.79 and 0.14. So let us see if the charges add up or not. So 200 oxygen are there and 93 Fe molecules are there. All right. In 200 oxygen molecules, the charge will be plus 400. And in 93 Fe molecules, we need to find out based on the percentage. So this says that the plus 2 and plus 4 ka plus 2 and plus 3 ka composition is plus 2 composition is 79 divided by 93 and plus 3 ka composition is 14 divided by 93. So if we find out the total number of plus 2 and plus 3, we will see that plus 2 is 79 and plus 3 is 14. Now we multiply them by their charges. 79 into 2 is 158 and 14 into 3 is your 42. So totally this comes as 200 and this is confirmed that yes, the thing matches with the number of oxygen molecules. So we will say that this is correct. Then Fe 0.930 is a metal deficient with lattice comprising of cubic close packed arrangement of oxygen ions. So this is basically of solid state of class 12. We will not cover this statement here. Next, the percentage composition of Fe plus 2 and Fe plus 3 is 85% and 15% respectively. So if we calculate the percent composition, so we will see that the statement is absolutely correct. Moving on to the next question. The number of units which are used to express the concentration of solutions from the following. So this is a direct question we had just seen, that mass percent, mole fraction, molarity, molality, and ppm also. All these are units which are used to express concentration of what? Which are used to express concentration of solutions. So we had just seen this. These are direct questions. How many? The number of units are 1, 2, 3, 4, 5. So 5 is the answer. Next question says, what is the mass ratio of ethylene glycol required for making 500 gram of 0.25 molar aqueous solution, 0.25 molar aqueous solution? So for first, we have 0.5 kilogram of 0.25 molar. So number of moles, if we try to find out, we have 125 by 1000 moles of ethylene glycol. Okay. And for the second one, we have 0.25 liters. And the number of moles will be 0.25 into, again, that 0.25 molar, that is equal to 625 divided by 10,000. And if we take the ratio of these two, which is 125 by 10 to the power 3 into 10 to the power 4 by 625. So it will be 2:1, right? We don't need to multiply and find out the mass because number of moles corresponds to the mass of these substances. So if we have 1 mole, the mass will be 62. If we have 2 moles, the mass will be 124. So we can just directly divide the moles because the molecular masses will cancel themselves. Again, we have the fourth question. The number of hydrogen atoms per molecule of a hydrocarbon having 85.8% of carbon is. So it says 85.8% carbon and approximately 14.2% hydrogen. So suppose we find out in 100 gram, this is the grams of carbon and this is the grams of hydrogen. So let us see how many carbon atoms can this make. We have 85.8 divided by 12, which is the molar mass, and for hydrogen it is 1. So 85.8 divided by 12, it gives 7.15 and 14.20. So approximately 7 carbon atoms and 14 hydrogen atoms can be seen, which gives us the simple ratio of 1:2 for carbon and hydrogen. So CH2 is the empirical formula. Now the molecular formula is given as 84. The more empirical mass of this thing is 14. So molecular mass will be 85 divided by 14. We have 6. So we multiply. If we multiply it by 6, we have the answer is CH2 into 6. C6H12. Okay. Next, when a hydrocarbon undergoes combustion in the presence of air, it requires 9.5 equivalents of oxygen and produces 3 equivalents of water. What is the molecular formula of A? So the question says that a hydrocarbon undergoes combustion in presence of air, which means oxygen is there. It requires 9.5 equivalents of oxygen and 3 equivalents of waters are produced. Let us first write the reaction. Suppose Cx, number of carbon is X and hydrogen is Y, plus oxygen gives CO2 and H2. So number of CO2 will definitely be X because number of carbons are X, and the number of H2O will be Y by 2. So number of oxygen used is X plus Y by 2. We simply need to put it in the equation. X plus Y by 2 is equal to 9.5. And it has produced 3 equivalents of water. So Y by 2 is equal to 3. Therefore, Y is equal to 6. We put Y is equal to 6 here. X plus X by 2 is equal to 9.5. This is 3, and this is 6.5. So X is equal to 6.5. Y is equal to 3. And if we take a whole ratio, X will be 13 and Y will be 6. So sorry, this was equivalents X plus Y by 2. I'm so sorry, there has been a calculation mistake. We'll do it again. Basically, I missed this part where here we have 2 oxygen molecules, right? So the total number of oxygen molecule is 2x plus Y by 2. Now, if we calculate, we know that Y is equal to 6. So 2x plus 6 by 2 is equal to 9.5. So 2x is equal to, if we subtract it, 6.5. So x is equal to 6.5 by 2. Y is equal to 6. So we multiply both of them by 2. So we have C8H6 as the answer. right? Next, when 0.01 mole of an organic compound containing 60% carbon was burned completely, 4.4 gram of CO2 was produced. Again, we need to find the molar mass. So 0.01 mole of organic compound, it has 60% of carbon. 60% of carbon means, let us find out the empirical formula first. 60 by 12 is carbon, which gives us a 5 term, and if 5 molecules and the rest 40, if we assume it as hydrogen, then we will divide it by 1, and this is like, I don't think it is a hydrocarbon, so we cannot assume, because 5 carbons cannot accommodate 40 hydrogen. So let's assume that 4.4 gram of CO2 was produced. What is the moles of CO2 produced? 4.4 upon 44, that is 0.1. So if 0.01 moles of compound produces 0.1 mole of CO2, so definitely the compound has 10 carbon atoms, because it is giving 10 times the CO2, right? The nearest molar mass of compound, if it has 10 carbon atoms, which amount to what grams? 10 into 12, 120 gram. And this 120 gram is basically 60% of the compound. So 0.6 of the compound is 120. So the compound is 120 by 0.6. So basically it is 200 grams. Okay. So we can compare it by the amount of carbon that has been produced in the compound. Next, let's move on to the 7th question. Some amount of dichloromethane, which is CH2Cl2, is added to this much amount of chloroform, which is CHCl3, to prepare this much molar of solution of CH2Cl2, dichloromethane. Concentration of dichloromethane is dash ppm by mass. So concentration by ppm is, by mass is, that is mass of dichloromethane divided by total mass, and we have to express in parts per million. So it has, what do we have? Some amount is added to chloroform, this much ml, and they have given density of chloroform. So we can find out mass of chloroform by the density. So if we multiply density into volume, that is 1.49 gram per ml into 671.141 ml, we can find out the mass. This exactly comes as 1000 grams. Okay. We will assume it as 1 kg of chloroform, CHCl3. And the molarity of the solution is 2.6, 10 to the power minus 3 molar. So molarity is moles of, here the solvent solute is DCM, dichloromethane, divided by volume of solution. This is the molarity. So moles of, we assume that X number of moles are there, and volume of solution is, it is given 671.141 into 10 to the power minus 3, because we have to take it in liters. So if we multiply 2.6 into 671.141, we get 1744 into 10 to the power minus 6. This is the number of moles of DCM, and we have to find what is the mass of these number of moles. So 71 plus 2 plus 12, which amounts to 85. We have the molecular mass is 85. So mass of dichloromethane, this is the moles of dichloromethane. So we multiply 1744 into 85. We have 148,240 into 10 to the power minus 6 grams. And if we remove the powers of 10, we will have 1.48 into 10 to the power minus 1 gram. This is the mass of dichloromethane. And if we divide it by 1000 grams, 1.48 into 10 to the power minus 1 divided by 10 to the power 3. So we will have a mass percentage, which is ppm. If we need to measure ppm, then this is 1.48 into 10 to the power minus 4. So 148 into 10 to the power minus 6. This corresponds to 148 ppm. So for 1 million grams of solution, we have 148 grams of dichloromethane. We move on to question number 8. This is the list of how to separate organic compounds. Okay, so chloroform, and this is a polar compound, so these should be this is aniline. Chloroform and aniline will be separated by distillation. Similarly, any organic compound in H2O will be separated by differential extraction. Fractional distillation is for compounds which are almost similar in your composition. We can put aniline and water for fractional distillation, and we can put these two. We can put these two non-polar compounds for fractional distillation, and aniline and water can be put for steam distillation. Okay, so option 2 is the correct option. Next question we have on complete combustion, 0.492 gram of an organic compound gave 0.792 gram of CO2. They need the percentage of carbon. So there has been a complete combustion and 0.792 gram of carbons has been released. If we divide it by 44.792 divided by 44, we have 0.018 moles. Suppose the addition of oxygen has been about 0.3 grams. 0.3 grams. This has been added. So the amount of carbon 0.492. This is a kind of a, I think some information is missing. Let me cross-check it with the solutions. Okay, so weight of carbon in 0.792 grams CO2, which is 12 divided by 44 into 0.792, 0.018 into 12. That is 0.216. gram of carbon. So this was the missing link. We can now calculate here also. So weight of carbon is 12 into 0.018, which is 0.216 grams. So we can easily find out the percentage of carbon now, which is 0.216 upon 0.492. This comes to be 44%. Okay. Zinc reacts with HCl to give hydrogen and zinc chloride. The volume of hydrogen gas, okay, we'll write the reaction first. Zinc plus HCl gives ZnCl2 plus H2. So we will have to put 2 here. The volume of H2 gas produced from the reaction of 11.5 gram of zinc with excess HCl is. So zinc, we have been given 11.5 gram. This is the limiting reagent because HCl is excess. So for one zinc, we have one H2 molecule. Let us calculate the moles of zinc. 11.5 divided by 60, 11.5 divided by 65.4, which gives us 0.18 moles. So similarly, 0.18 moles of H2 will be produced. And the volume of hydrogen gas at STP. So we have the moles. We will multiply it by 22.7, which will give us the value of approx 4 liter. So 4 liter hydrogen. Next, when a hydrocarbon A undergoes complete combustion, it requires 11 equivalents of oxygen. Hydrocarbon, so CXHY again plus O2. O2 has been given 11. It should give XCO2 and Y by 2 H2O. Right? If Y hydrogen are there, then Y by 2 H2O. So total oxygen should be 2x plus Y by 2, right? And it has been given as 11. 4 equivalents of water. Water, if we see the equivalent weight of water, we need 2. Again, multiplied by 2. How many moles of water has been produced? If 4 equivalents of water are there, it will be 2 moles of water, because n factor for water is 2. As plus 2 say, it is going to 0. So it will be 2. Now, they have said that 2 y by 2 is equal to 2. So y is equal to 4. We put that in the second. 2x plus 4 by 2 is equal to 11. 2x is equal to 9. X is equal to 4.5. 4.5 and 4, we multiply both by 2. So we get C9H8. Next, assume carbon burns according to the following equation. Carbon plus oxygen gives carbon monoxide. When 12 gram has been burnt in 48 gram of oxygen, the volume of carbon monoxide produced. So if 12 gram has been burnt, how many moles have been burnt? 1 mole. And if 1 mole has been burnt, so 1 mole of CO will be produced. We can see it from the equation. 2 moles burns, 2 moles produced. So 1 burns, 1 mole has been produced. Now the volume has been, we have to just multiply it by 22.7 into 1. So 22.7 liter, and it is equal to 2.27 into, sorry, 227 into 10 to the power 1 liter. So this is 227. Moving on, we move to the next question. The density of 3 molar solution of NaCl is 1 gram per mole. The molality of the solution is So we have to find the molality. Density is 1 gram per ml. Now, nearest integer, if we suppose if we take 3 moles of NaCl, put it in 1 liter of water, that will be 3 molar. Okay. And in 3 molar, there are 1000 ml of solution. So let us find out the mass of NaCl in 3 moles. That it should be 58.5 into 3, that is 175.5 gram. And the density is given. Density is 1 gram per ml. So 175.5 ml. This is the mass of, this is the volume of NaCl. So the volume of solvent is 824.5 ml. This is the solvent. So we just need to, this is also the solvent in grams because of the density. We just need to divide 3 by 0.8245. So the answer will be 3.63 molar, or 363 into 10 to the power minus 2 molar. Last question is molality of a 10% volume by volume solution. Dibromine in CCl4 is X. So if 10 ml of Br2 is there, then 90 ml of CCl4 will be there. That means 10% volume by volume. Now molality has been given and they are asking for the molarity. So molarity is moles Br2 divided by volume of solution. So let us assume that 100 ml of solution is there. For 100 ml of solution, we have 10 ml of Br2. Okay. 10 ml of Br2, the density of dibromine has been given 3.2 gram per ml. So for 10 ml, the mass will be 332 gram. So moles will be 32 by 160. That is 0.2. So 0.2 by 0.1, that is, because 100 ml is there, so volume is 0.1. Mole to 0.2 are the moles. That gives us 2. So 200 into 10 to the power minus 2 molar. So this was all with your some basic concepts of chemistry. So basically, we have finished this chapter. We will just go and look at the summary once more. So chemistry is not a very old discipline. It started as an alchemy, but before that, it was just a vague subject and very different kind of methods were used. Now, study of chemistry is important. Classification of matter into mixtures and pure substances. Mixtures are homogeneous and heterogeneous. Pure substances are elements or compounds. Element can be as an atoms or molecule. Now, properties of the substance, physical properties and chemical properties. Physical properties are the one which do not require you to change the composition or the identity of the chemical. And chemical properties need you to change the identity of the chemical in order to show what kind of chemical reactions these compounds are showing, right? Then there are systems of measurement, which right now we are using SI units for physical properties. There are 7 fundamental units, right? We have the mass, we have length, we have time, we have temperature, we have luminous intensity, we have amount of substance, we have current. These are the 7 fundamental systems. They have their SI units. Now for again, we have your scientific notation, we have significant figures, we had seen the rules, dimensional analysis. These are basically covered in your physics, so no need to worry about them in chemistry here. The thing which you need to know in this chapter, one more important thing is the laws of chemical combinations, law of conservation of mass, okay, law of definite proportions, law of multiple proportions, Gay-Lussac's law of gaseous volumes, and Avogadro's law. These 5 laws you need to remember, which scientists have given these laws and what these laws say. According to that, you need to answer. Then there is the Dalton's atomic theory, very easy. Atomic mass, average atomic mass, molecular formula, and formula mass. All these are important. Then we define mole. What a mole is, we need to define it. So this mole thing is basically the amount of substance, and 1 mole, just like 1 meter is the light length of a light traveled, the length that light travel in 1 divided by whatever the unit is. Similarly, the 1 mole is defined as 6.022 into 10 to the power 23 atoms, and this number is known as the Avogadro constant. It is known as 1 mole of the respective particle or entities. Okay, chemical reactions represent the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lot of information. The coefficients of these elements and compounds in the balanced chemical reactions, they indicate the molar ratios and respective number of particles taking part in a particular reaction. So if we have C plus O2 gives CO2, then it says that 1 carbon element, 1 carbon atom, and 1 oxygen atom, 1 oxygen molecule, which is O2, will combine to form 1 CO2 molecule, which is 1 CO2. If we have H2 plus 1 by 2 O2 gives 1 H2O. It says that 1 hydrogen molecule and half of oxygen molecule will be combined to form 1 water molecule. Or we can say 2 hydrogen molecule and 1 oxygen molecule will give 2 water molecules. The quantitative study of these reactions required for the products formed is called stoichiometry. Using stoichiometric calculation, the amount of 1 or more reactants required to produce a particular amount of product can be determined, and vice versa. The amount of substances present in a given volume of solution is expressed in a number of ways. For example, mass percent, mole fraction, molarity, and molality. So this was all about your chapter basic concepts of chemistry. Thank you.